Similarly, there are certain quantitation errors. That is, you have wrongly integrated the peak area, or the baseline was not smooth. It was like this. It was like this. So because of this, certain errors occurs. Similarly, coelution also occurs. Coelution. So again, programming, you can do temperature programming to solve all these. Similarly, there are certain cases of peak convulsions like this. So you have to do peak deconvulsion like this by using certain programs. So if you do peak deconvulsion, you will get like this. By using certain computer based programs. So you drop perpendicular in these peaks and then you run certain programs and you get finally this well separated good baseline peaks. So let us do certain numerical to clear all the all our issues. For example, consider that total overlapped area is 5000. That is, you have a situation where two components are coming and they have certain common area like this. So the common area is, or you can say overlapped area, because if you are going to interpolate, then what you are going to do, your peak like this. So these are the overlapping areas. So overlapping area is 5000. Now the software assigned 65% to A, for example this component, and 35% to this component. So A may be calculated to be 3250, because 65% of 5000 comes out to be 3250. Similarly, 35% of this comes out to be 1750. So this is how you actually quantify, or you can actually clean or rectify your errors. Now the column bleed and stability. As we have already talked, that column bleed is actually a problem, because in certain cases you have to vaporize a sample and that sample has a high boiling point. So in order to have a good resolution, in order to have perfect elution, you have to raise the temperature, and at a certain temperature, beyond that your stationary phase also starts decomposing, and the moment it starts decomposing, it also starts eluting along with the sample, and this elution is called as the column bleed. So you have to have very stable stationary phase. So you have to have very stable stationary phase so that you can avoid the column bleed. So high baseline gives you column bleed, and column bleed means that your stationary phase has just break down. It has actually gets unstabilized and the stationary phase is no more uniform and it is no more spreaded uniformly. So at that situation, you have to replace your stationary phase and you have to work for next run, you have to work at lower temperature. So the solution is you have to avoid maximum temperature and you have to use low bleed phases. For example, if you just add phenyl, then you actually stabilize it more. So you have to work for certain additives so that you can get more stabilized stationary phase. Now there are certain issues, specific issues with the specific detectors. For example, FID was a very good detector in terms of sensitivity, in terms of linear response time. It was exceptionally good. But the problem is that it actually works on the principle of combustion, because it's a detector which consumes, which burns the sample, which combustions, where the combustion of your sample occurs. So here, because you are using flame, so there is always chances of flame instability. So you have to make sure that your flame is maintained or lighting at the same efficiency. It is lighting at the same efficiency. Similarly, in cases of TCD, there are chances of filament burnout, because there are two cavities in the TCD. In one cavity, it is only the carrier gas which is flowing, while in the other cavity, it was actually the effluent along with the carrier gas. So you have to make sure that the temperature should not rise too much. Otherwise, the filament, which is generally made up of tungsten, may burn out. Similarly, when you are doing the mass spectrometry, So you have to check that all the ions should correspond to all the analytes. You have to check for dirty ion source also. So what is the solution? Solution is again there. You have to do the maintenance on a regular basis, and on the regular basis you have to also do the calibrations each time, after maybe weeks or after maybe months, depending upon the use of your gas chromatograph. You have to do the maintenance and you have to do calibrations then time and again. So let us study few cases. For example, the hydrocarbon mixture. Now if you are using a isothermal system or isothermal oven, then you actually get poor separation of heavy compounds because they are actually having high boiling point. So always you have to, in case of heavy compounds or you can say the compounds which have high boiling point, you always use a temperature programmed ovens. Temperature program. We have already discussed it. Temperature programmed ovens or temperature programmed, you can say, columns also. Because by using the temperature programmed column, you get well resolved peaks in less time. In less time also. Time is money, okay? So you have to make sure that the time is as minimum as possible. So the lesson is that method development must match the analyte range. That you should know that what type of analyte you are actually using. For example, here you are using hydrocarbon mixture, which is actually non-polar and low boiling also. Low boiling. But after carbon 20 range, boiling range increases. So you have to make sure about your nature of your analyte, okay? Similarly, let us see a case study involving pesticides, where we have to check the pesticide residues in a food sample. So now you have to check about the internal standard, and you have to also ensure that which type of standard you are adding, so that you can suppress the effect of the matrix. So for external calibration, if you get a result of 0.052 ppm, 0.052 ppm, and the internal standard which you have corrected is 0.049, then if you divide it, you will get an error percent of 5.8, that is 2% reduction. So you have to check for the internal standards also. Similarly, a blood alcohol determination. If you have an internal standard of N-propanol and you calibrate it with respect to volume, for example, with respect to ethanol, it ranges from 0.01 to 0.40, then the GC will result 0.0085% ethanol. So it is actually a limit which is legally significant and clinically it is good. So each time you have to check for the response. Similarly, if you are integrating GC and MS, that is mass spectrometer, then actually you are using a hyphenated technique. So by GC you actually identify the unknown compound, and by using the mass along with GC, if you are coupling your the mass spectrometry with GC, then you can also get the structural information. So chromatographic separation from GC combined with the molecular identification from MS, you get a complete information about your unknown analyte. And this GCMS integrated technique or hyphenated technique is used in forensic toxicology, anti-doping, environmental monitoring, and also in certain cases of mishappenings, deaths, where you have to, and where a person or a dead body has to undergo post-mortem. So GCMS also comes to play to check the poisoning. Now you can always use certain software, and nowadays you can use one of the striking technology, that is the artificial intelligence solution. So by using software and the AI, you can get automated peak integration. So there are actually, this automation helps you to minimize the manual integration errors. Similarly, you can undergo you can ascertain the puke purity checks. And because now you have a library, library means you have a big data of samples. So every time if you have if you have to identify a certain new compound, then you always check the parameters in terms of, for example, in terms of TR, in terms of alpha and other things with your previously reported compound. That is called as the library search, just to make sure that whether your compound was already known or it is a new compound. Similarly, you can do the AI based search with regard to retention times. Okay, so you can predict that whether this compound is this or not this on the basis of the TR values. Now let us solve a problem. You have a GC at an isothermal condition, that is the temperature is maintained, and the retention times for N-hexane is coming out to be 6.2 minutes. You have another compound, that is N-heptane. Now this hexane, which consists of 6 carbon, the retention times comes out to be 6.2 minutes. For N-heptane, which is having 7 carbon atoms, the retention time comes up to be 8.35 minutes. Now there is a presence of an unknown compound whose retention time you have calculated and it is given to you, that is 7.5 minutes. Now on the basis of covariant retention index, that is Ri, you have to identify the unknown compound. So you have to use the formula which we have discussed previously. Now you have these values, you put on the formula which we already discussed. Now when you solve it, your reading comes out to be 663.8. Now this 663 is actually, if you round off, you will get 664. So this value actually comes out to be somewhere between, you can say that somewhere it is less than 700 but greater than 600. So you are sure that since it is greater than 600, so there must be at least 6 carbon atoms. But since at the same time it is less than 700, so the carbon atoms must not be 7. So when you actually resolve it, you will find that it is a branched hexane derivative. So on the basis of this value, and because this covariant index is very sensitive with regard to the number of carbon atoms, and this covariant was actually, it was developed by Swiss Hungarian chemist Erich Kovet, and he found that this covariant index is very sensitive with regard to change in chain length of carbon atoms. The moment you change one carbon atom, the value changes very, you can say, very methodologically. 700, that is, it changes in a very gradual fashion, in a very regular fashion rather, you can say. So in a regular fashion, since it is changing in a regular fashion, so you can predict for 10 carbon the value must comes out to be, covariant index comes out to be 1000. For 12 carbon it is to be close to 1200. Since it is coming in a regular, it is changing in a regular fashion, so that is why they developed it for alkanes. Similarly, you have another problem. Now here you have given an analyte, that is X, and an internal standard which we represent by IS. So you have given the peak area for analyte and the peak area for the internal standards. Concentration of internal standard is given to you and response time is again given to you. So you have the previously we have discussed the RF actually is AX upon CX upon AIS upon CIS. So when you reshuffle it, you will get this in terms of Cx, because we have to calculate Cx. So when you input all these quantities here, you will get a value of 1.45 milligram per ml. So this is how you have calculated the concentration of your analyte. So here you have given the area of analyte and you have calculated, your area is given to you. That's area is actually this one. And the area of the analyte is also given to you. Not the area of analyte, but the area of internal standard. So this is how you have calculated it very intelligently, the concentration of your analyte. Okay. So another problem, it is the old problem which we have already discussed. Here you have a two component system which you have run from GC. You have analyzed this two component system from a GC, and you get the retention time for component A as 5.25 minutes with a width, peak width, or you can say peak width of 20 minutes. Similarly, you have TRB, and this is also 0.22 minute. Now you have the formula where you have calculated the resolution twice of TR2 minus TR1 upon W2, width of peak of component 1 plus width of peak of component 2. Now you have to make this again in your mind that this is actually 2 stands for that component which is eluting last. That is why TR2 minus TR1, and this is actually W1 and this is actually W2. So you input your values in this formula and you get 3.57, that is RS is 3.57, which is greater than 1.5. That is, now on the basis of this RS value you can say that you have a very good baseline separation. You can see that this is the baseline separation. That is, the two peaks are differentiated straight from the baseline. That is called as the baseline separation. So whether the baseline separation is achieved? Yes, baseline separation is achieved on the basis of the value of 3.57. So this is how you actually calculate, and you actually tells that how efficient your GC run is. So another problem, that during a pharmaceutical GC assay, peak shows significant tailing. Now if the tailing is there, that is, you have a situation like this, tailing is occurring. So what are the probable causes and what are the solutions? Okay, so we have to locate first the causes and then we have to check for the solutions. So the first probable cause may be that the active sites in the column have interacted strongly with the compound. If your analyte is polar, then their stationary phase must be polar. Because of that, the interaction will be stronger. So the active site is blocked or it is having a strong interaction. So solution is, you have to deactivate your liners or the guard column, or you have to do certain selenization. You have to use certain selenyl compounds, so that, because for example if you have like this selenol, okay, if you have a polar, this is actually very polar because of the presence of OH groups. So here it is, this is polyselenol. Now if your, for example, if your stationary phase is polar, then what you do, you just run your column by this compound and all the polar will attract here, and it will be removed. So next time when you run the column, when you run the GC, there will be no peak tailing. You will get ideal peak like this. Similarly, the above other probable cause may be this one, that is, your stationary phase will be contaminated. So you have to, in that case, you have to replace your stationary phase. So the answer is, tailing is caused by active sites blocking or because of the contamination, and that can be solved by deactivation or by replacing or by doing the maintenance of your stationary phase. So this is how you actually solve the real life problems. Similarly, another problem, that your calibration curve of toluene, which is external standard method, gave you slope, that is, you are using the same y is equal to mx plus c. You have a calibration plot and it is cutting like this. This c is the response which we have noted, and this is the detector response, slope m. So m is given to you, c is given to you, that is called as the background response of column. This is c, up to this point, this is C, this is actually X, and this is Y. This Y is area under the peak of analyte. This is concentration of analyte. Concentration of analyte. So you just put all these things here because you have to calculate the concentration of toluene. So you just put it all here. So you have to calculate X here. That is the concentration. Here it is toluene. So you just put all these things here and you get X is equal to 5 milligram per ml. So this is how you actually solved your problem of detecting the concentration of toluene. Let us do another problem. Now you have a blank GC run. So blank GC run means there is no you can say sample, and your still shows peak at 9.5 and 12 minute. That it is showing peaks at 9.5 minute and 12 minute. So what are the likely causes? And you have not introduced your sample yet, okay, without injection. So these two peaks are coming. The first cause may be your septum has bleeded. Your septum has bleeded. That is, on increased temperature, your septum has, along with the carrier gas, has gone into the column and it is showing peak. Similarly, another probable cause may be column contamination. There may be some leftover you can say analyte of the previous runs that is coming. So you have to perform column breakout. Similarly, if there was a septum bleed, then you have to replace your septum. Another cause may be injector carryover. So you have to clean your liner and you have to reduce your sample volume. So the final answer is these ghost peaks may be due to the contamination, it may be due to the carryover, or how you are going to resolve it: by septum replacement, by breakout, by cleaning injection system. So you have to look for all these issues from time to time so that your column or your GC remains efficiently working. So another problem, a GC calibration give the following regression statistics. Here the standard deviation of blank is 50 area units, and your slope of calibration, which is defined by M, is 2000 area per milligram per ml. So you have to have two formulas, that is limit of detection and limit of quantification. So you have to calculate, and the formula is 3 sigma upon m and 10 sigma upon m. So you calculate it individually, you will get the limit of detection is 0.075 milligram per ml. That is, this is the quantity which your detector is detecting. This is the quantity which is actually detected by detector, whatever detector you are using. But this quantity is not getting transformed into a signal. And this LOQ is that quantity which is detected and also transformed into a signal. You can see this. So you can see a difference in the value. This value is big, and that is why it comes as a peak. This value is so small that although your detector is detecting it, but it is not getting any peak. It is not coming in the form of peak. No peak is there. But this is coming as a peak. Okay. So you have to make sure. Another problem, that in a forensic analysis of GC for ethanol in blood, the following data is obtained. That is, area of ethanol, area of internal standard, it is 4000, area of your analyte is 4200, the retention factor is 0.98. So you have to calculate the concentration of your analyte, which is ethanol in this case. So you have the formula, that is RF was, if you remember, RF was AX upon CX upon AIS upon CIS, where A is actually, A is the area under the analyte, AIS is the area under the internal standard, CX is the concentration of analyte, and CIS is the concentration of your internal standard. So you put all these and you reshuffle this. If you populate all your values in this expression, then you will get as 1.07 milligram per ml. That is actually the concentration of ethanol. So with this, we have covered a lot of problems and we have discussed all the theories of elution chromatography, of gas chromatography, and we have solved certain problems. And now the floor is open for discussion as well as for any issues, for any queries with you. Thank you all, and we are going to meet again while we are discussing the HPLC, that is the high performance liquid chromatography. Till then, thank you.